Alrighty, hello lovely Year 12s. Today we're looking at Sadler's Chapter 5c, which is the vector equation of a line and plane. We're pretty much just building on everything from Chapter 4 in this chapter. So we had a look at everything in vectors in 2D, and now we're doing everything all again in 3D. So first of all, we're going to look at the vector equation of a line first, followed by a plane. So just looking at the vector equation of a line in 3D, it is the same rule for the vector equation of a line in 2D. It applies to 3D. So that is a point on the line R is defined by A plus lambda B, where A is a point on the line and B is a vector parallel to the line. And lambda is a scalar amount, and generally in context, it's generally time. So previously, when we were looking at vectors in 2D, the scalar product form of the vector equation of a straight line, r dot n is equal to c, that one does not work in 3D. So we're just using the r is equal to a plus lambda b. So let's just have a look at a couple of questions here. So for our first one, for this example here, a line passes through the point with position vector 2i, take j plus 3k, and is parallel to the vector I plus j plus k. And we want to figure out the vector equation of the line. So that's just nice and easy. This is essentially, this is our a vector there, and this is our b vector there. So it's pretty much just putting that into the equation. So I'm just going to say r is equal to my starting position. So that is 2, -1, 3 plus some constant amount lambda of 1, 1, 1. That's the 1i plus 1j plus 1k. Cool. And so we can write that as a single vector. So I could go, well, that's just 2 plus lambda, -1 plus lambda, and 3 plus lambda, like so. So we've got that there. And it's also asking us to write that as a parametric equation. So remember that R represents a x, y, and z coordinate, and so that's equal to 2 plus lambda, -1 plus lambda, and then 3 plus lambda. So as a parametric equation, we'll just write it as x is equal to 2 plus lambda, y is equal to -1 plus lambda, and z is equal to 3 plus lambda. And you can figure out the Cartesian equation in 3D, but it's not required here. So we'll just leave it like that there. So that's those two parts there. Here is a second example, which we'll go through now. And that is to show that the lines L1 and L2 there intersect, and find the position of the point of intersection. So we've got them there. So if they do intersect, then essentially they have to equal one another. So basically I'm going to write out both lines. So let's do that here. We're going to say we've got 7, 3 minus 2 plus 2 lambda plus 4 lambda, take lambda, that is equal to, let's put in the 0 there, 0 plus mu, just got here -1, and 14, take 3 mu, like that there. Okay. So both of those two lines there, they both, we've got lambda in L1 and we've got mu in L2, and that's because we don't know what, they can have different coefficients, so they could be different starting times, whatever. So we need to solve simultaneously to determine what lambda and mu is going to be, and that'll tell us where those two lines intersect with one another. So I'll just write out three sort of equations from that. So 7 plus 2 lambda is equal to mu. 3 plus 4 lambda is equal to -1, and minus 2 take lambda is equal to 14, take 3 mu. So from our second equation, so I'm just going to write these here. These are our three equations. So from equation 2, we can say that, well, 4 lambda is equal to -4, so lambda must be equal to -1. So I'm going to sub that into equation 1, and then I can say, well, 7 take 2 is equal to mu, so that means mu is equal to 5. Now let's verify with our third equation here. So if I substituted lambda and mu into the third one, we're going to have, that would give us, let's do this in a different color here. So that would be -2 plus 1 is equal to 14. Take 3 lots of 5, and that's -1, and yep, -1. So yeah, that works. So we'll verify that that's true for that one there. So we figured out the values of that there. So essentially, we just have to put that in to figure out where the point of intersection is. So I might just focus on the second one here. So if I put in, so R is going to equal to, now for mu is equal to 5, so 5 lots of 1 is 5, 5 lots of 0 is 0, and 5 lots of -3 is -15. So that would be the, oops, sorry, just want to go back here. So that would be 0 plus 5 minus 1, and then 14 take 15. So that would be 5, -1, -1. That would be the point of intersection where the two lines meet for that one there. Cool, awesome. So that's a vector equation of line in 3D. Now we're going to have a look at the vector equation of a plane in 3D. And this can be found knowing a few different things. So first of all is you need a starting point on the plane, or just like any particular point that exists on the plane. And then you also need two non-parallel vectors that's parallel to the plane. And so essentially, if you have some scalar amount of one of those vectors and another scalar amount of the other vector plus the starting position, that'll give you the equation of the plane. And you can see that in the diagram there. So you've got two vectors B and C, which are parallel to the plane. You've got lambda amount of B, mu amount of C, and vector A, that's your starting position on the plane there. And so there you can then basically come up with the equation of a plane. You can also define a plane by just having a single point on the plane and then a vector perpendicular to the plane, because then the difference between any point on the plane and A is going to give you a line, and then which is going to be on the plane. And then if you did the dot product of that and the normal vector, that should equal to 0. And so essentially this is just like the scalar product form of the equation of a line. And however, you can apply it for a plane here, like that there. Alrighty, so we're going to have a look at some example questions where we can work with planes now. And so we've got here a line has a vector equation of that. Plane has its vector equation, and then we want to show that point A is a position that lies on both the line and the plane. Okay, this is some new notation that you'll be familiar with. So if you see something like that there, that indicates that that is a plane, and generally we use L for a line. Okay, so if a point exists on a point or a plane, if you substitute it in, it should, the equation should be true for that there. So let's put it into the line. So let's sub in 1, 5, 1 into L and the plane. So in the line, we're going to get 151 is equal to 7, 3, 5 plus lambda amounts of 3, -1, and 2. So basically you've got 3 equations going there. So you would have 1 is equal to 7 plus 3 lambda. So that means lambda would be equal to -2. 5 is equal to 3 take lambda. So that's 2. Yep. So lambda again in that second line would equal to -2. And the third line, 1 is equal to 5 plus 2 lambda. So 2 lambda is equal to -4. So lambda's got to be -2. So that is true because at that particular point, lambda is the same for all of them. If you got a different value for lambda, that would not be true. And now if we were to put it into the plane, I would get, all right, 151 dot 5, 3 minus 6. That should equal to 14. So let's check, see if it works. 1 times 5 is 5. 3 5s are 15. 1 6 is 6. So take 6 is 14. Yep, 20 take 6 is 14. Yep, so that's true there as well, that works. Now, show that the line lies on the plane. So to prove that a line lies in a plane, we need to show that the 2 points from the line fall on the plane. So here we know point A, and that's when lambda is equal to 2, lies on the plane. So yes, we know that 1, 5, 1, that does lie on the plane. We've already shown that. So if we show another point from the line lies on the plane, then we'd say that that's true as well. So this is, we just did part A, and now we'll do part B. So basically we want to show a second point of the line lies on the plane. So let's get a second point. And so let's just say when lambda is equal to 0, what are we going to get? So that's just going to give us 7, 3, 5. So that gives us the point lambda is going to be equal to 7, 3, 5. And let's check to see if that works as well. So, so when we let's think about this here. So let's put that into the equation. So for the plane, and so if we say 7, 3, 5 dot 5, 3 minus 6, what does that give us? That gives us 35 plus 9, take, not 13, 30, take 30. It says 44 take 30 is equal to 14, which is what it should equal to as well. So we've shown that two points of the line fall on the plane, so therefore L falls on the plane. Okay, so we can say that's true. Here is a third example now. So what we've got here is we want to find the vector equation of a plane containing a line and a point. Okay, so let's do a little diagram to sort of visualize what's going on here. So essentially, picture that is our plane. We've got a particular point, and that's going to be our, -1, 5, 3. And then we're also going to have a line which is defined by -1, 3, 5 plus lambda -1, like so there. So essentially, if we come back up here and we think about how do we define a plane, you need a starting point and two lines. And if we look at what we've got here, we've got a starting point and one line, but I can pretty much create a second line there by just going from that point to the start of that line there. So all I've got to do is basically my second line can be found if we substitute 0 into that line there. That'll give us our starting point. So that particular starting point there is just going to be -1, 3, 5. And so our second line is just going to be r is equal to -1, 3, 5, and take away our other point there. So -1, 5, 3, and what does that give us? 0, -2, and 2, like so there. Cool. So we've got that there, and so essentially all we can do is just go, all right, well, so this is our line, so our plane is going to be equal to our starting point, -1, 5, 3, plus some lambda amount of 2, 4, -1, plus some other amount of 0, -2, 2. And you might be wondering, I did, this -1, 3, 5 take away -1, 5, 3. If you did it the other way, would it really matter? And well, if you did it the other way around, you get the negative of this. You get 0, 2, -2. But keep in mind, that's a scalar amount, and that scalar amount can be positive, negative, anything. So it just essentially would cancel it out. So you can get different variations of that as well. So there's technically really infinite possibilities of what this equation is going to look like. And when you apply the equation into a context in some future examples we'll look at, you'll notice that it doesn't really matter, but because you can have scalar amounts of all of this and it would still work. Alrighty. Another example here, find the position vector of a point where the line meets the plane. There, so we've got a line and a plane, and I want to find what that point is. And so essentially, I'm just going to rewrite this out. So let's do, I'll change color again. So let's see here, we've got a line. So 2 plus lambda, 3 plus 4 lambda minus 1, take 2 lambda. And that's our line. And then our plane, dot 3, 1, 1 is equal to 1. So if they meet, then essentially what we do is if we substitute this line into the equation for the plane, we can then expand it and then go ahead and solve for lambda to find out where they intersect. So basically, sub in line into plane. That's what we're going to do. So that's going to give us 2 plus lambda, 3 plus 4 lambda, negative 1, take 2 lambda, dot minus 3, 1, 1 is equal to 1. So let's go ahead and do the dot product here. So I'm going to have minus 3, 2 plus lambda, plus 3 plus 4 lambda, plus negative 1, take 2 lambda is equal to 1. And yeah, you can just put in your class pad and solve it. Let's just go ahead and do it manually here. Take 3 lambda plus 4 lambda, take lambda, take 2, take 1, take 2 lambda is equal to 1. Minus 3, so 1, take 2 lambda is, so negative lambda is equal to, so minus 6 and 3, minus 3, minus 4, whatever that is 5, so that's equal to negative 5. Okay, now, and then if we want to find the point where that intersects, well, we put it into our original equation. So it's going to be 2 take 5, 3 plus 4 lots of minus 5, and negative 1 take 2 lots of minus 5. And we go ahead and we solve that. So we're going to get minus 3, minus 17, and 10 take 1 is 9. Cool. That's it there. Now, just one more example to go through with you. And so that is how to figure out the vector equation of a line given 3 points. And so this is nice and simple because essentially what we're doing here is if we've got 3 points, you've got any one of those 3 can be your starting position. So that can be your sort of vector A, and then you can create 2 lines using the other ones as well. So you might go, all right, well, I'm going to make that a line there and that a line there. Or you could go, oh, that's a line there and that's a line there. So it's up to you how you sort of do it. Infinite possibilities here for this. So let's go ahead and do that. So we've got 3 vectors. Got 3 vectors there. So I'm just going to list them out. I'm going to go, all right, I'm going to go a different color. This one here. So we have negative 2, negative 2, 1. We've got 10 minus 6 minus 3. And we've got negative 9, 5, 4. Okay. These are our points. I'm going to call this point 1, point 2, point 3. Okay. So essentially we can do this a few different ways. And so first way we can do this is we can go, all right, I'm going to do 2 take 1, and that's going to leave me with the line 12 minus 4 and minus 4. I'm also going to do line 3 take 2, and that's going to give me minus 7. It's going to give me, oh, not minus 7. 3 take 2 is minus 19. 5, that's going to be 11, and 7 there. Okay, so I've got those ones there. So then I can say, well, R is just going to be a starting point, so it's going to be my first one there. I'm going to be at minus 2, 1, plus some lambda amount of 12 minus 4 minus 4, plus some mu amount of negative 19, 11, 7. So nice and simple, doing that there. What I can do is I can put that into parametric form. So I can say that, well, okay, my x, y, z is going to be equal to minus 2 plus 12 lambda take 19 mu minus 2, just take 4 lambda plus 11 mu, and then 1 take 4 lambda plus 7 mu, like so. And then we can just solve simultaneously. I can see here that if I add a couple of these, or basically if I call that 1, 2, 3, if I did 2 take 3, that's going to give me y take z is equal to minus 3 plus 4 mu. If I did 1 plus 3 lots of 3, that would give me x plus 3z is equal to 1 plus 2 mu. If I was to rearrange both of these, that would give me mu is equal to y take z plus 3 over 4. This would give me mu is equal to x plus 3z take 1 over 2. Then you could equate them both together. Keep in mind, you can all do this. You could just go straight to, you could just solve on ClassPad to make it easier. I doubt you'd have to be doing this manually, but I'm just showing you anyway. Y take z plus 3 over 4 is equal to x plus 3z take 1 over 2, and multiply everything by 4, and you'd get y take z plus 3 is equal to 2x plus 6z take 2. So then that would give you the equation 2x take y plus 7 is equal to 5. Okay, so the equation of a plane is sort of a linear amount of x, y, z, and it's equal to a particular value like that there. So that's our that's one of the solutions there. This was one of the other ones as well. And yeah, so that's one way of doing it. Now, What we could also do is if we come back and think back up to here where we've got our 3 points, we can go ahead and just substitute each of those 3 points into our first equation there. So these represents x, y, z. So let's put all 3 points into our ax plus by plus zz is equal to d equation. So I'm just going to rule this off again. I'm just going to do it a different way now. So our points were, so we want to put it into the equation. Minus 2a, so basically putting it into the equation, ax plus by plus cz is equal to d. So each of those points, so that would give us minus 2a, take 2b plus c is equal to d. Our second point would give us 10a take 6b take 3c is equal to d. And our third one, 9a plus 5b plus 4c is equal to d. Okay, now we can solve for a, b, and c. That would give us three different values here. So it would have a is equal to 2d over 5. B would equal to minus d over 5. C would equal to 7d over 5. And just if you did that on the class pad there, and then if you were to put that into your original equation, so back up to this, back up to here, what we would get is, so AX, so basically we're going to get 2xd over 5, take dy over 5, plus 7 dz over 5 is equal to d. And then we go, oh, okay, well, d is common to everything, so I can divide everything by d, and I can multiply everything by 5. If I do that, I would get 2x take y plus 7z is equal to 5. And then we look at that, and I go, oh, that looks familiar. That looks exactly the same as the equation we've just come up there. So a different way of doing it, we can put it into the equation of a plane and then just solve simultaneously like that there. So now that we've got that there, what you think about, well, actually we can just convert that straight to, this form here. So into this equation here, that's what we're going to do now. So we're going to think, well, if I did the dot product of my x, y, z by 2, -1, 7 is equal to 5, that would give me this equation which we've just got up here, because x times 2 is 2x, y times -1 is minus y, z times 7 is equal to z is equal to 5, and x, y, z, well, that is our there. So we can just go back to this form here. It's equal to 5, like so there. Okay, so that's our third and final form there for our vector equation of line. All right, hopefully this has been helpful. Pretty massive video, but yeah, enjoy.